Okay, so this is the Applied Maths Higher Level paper for 2025, question 9a. So a car uses cruise control and is traveling with constant velocity 50 kilometers per hour. The driver sees a traffic light 60 meters ahead change from green to orange. The driver takes half a second to react to this. Calculate the constant deceleration required to stop the car at the light. Okay, so if we have a look first of all at the velocity, which is 50 kilometers per hour. We need to change that to meters per second. So we've got 50 kilometers, so that's 50,000 meters per hour. And then there are 3,600 seconds in an hour. So we've got to divide by 3,600. So we get 125 over 9 meters per second. So we've got to work out, first of all, the distance that the car travels in the first half second. So distance is speed times time. So distance is speed times time. So we have the speed of 125 over 9. Multiply that by the time, which is 0.5 of a second. So we get a distance traveled in the first half second of 125 over 18, and that is meters. So what we've got to do now is just work out the remaining distance. So let's look at that. So we know that there were 60 meters in total. So all we've got to do is, this is the remaining distance. So all we've got to do now then is just take 60 and subtract 125 over 18 meters. And we should get 955 over 18 meters. So now what we've got to do is work out the deceleration. So we're going to use v squared is equal to u squared plus 2as. The final velocity is 0 because it comes to a halt. The initial velocity is 125 over 9 meters per second, which we've got to square. And then we've got twice, and then we've got to multiply that by a. And then the distance is 955 over 18 meters. So all you've got to do is manipulate that, get a on its own, and you do get an acceleration of minus 1.818 meters per second squared, or a deceleration of 1.818 meters per second squared. That's the 3 decimal places. Okay, so this is part 2. Using the axis below, draw a displacement time graph for the motion of the car from when the driver sees the traffic light change. Relevant calculations should be shown in the space provided. Okay, so I've done this one out already just to save some time, so let me just run through it. We have here, this is the graph that you'll end up with, but we have the distance remaining after the first 0.5 seconds is 955 over 18 meters, so it's roughly 53.06. So that's this point here. So this part here is a straight line. After that, he starts to decelerate. So we're going to get this curve here. So let's work out these individual points. So let's see, the first one then is 0.5 seconds of deceleration. So I'm just going to look at 0.5 seconds of deceleration. Remember as well that the distance remaining after 0.5 seconds is 955 over 18 meters. So that's the distance of deceleration, if you like. 0.5 seconds of deceleration, then we're going to use this formula here, s equal to ut plus half at squared. The distance that he travels in 0.5 of a second while decelerating is his initial velocity u, which is 125 over 9, times 0.5 minus, because he's decelerating, a half. And I'm using the acceleration or the deceleration to 3 decimal places, 1.818, because I won't be able to plot the displacement on the graph very accurately to any more decimal places. So we have 1.818, 0.5 squared, and when you do that you get 6.718 meters. So that's the distance that is traveled during deceleration in the first half second. So that means the distance remaining then is going to be this distance here, 955 over 18, minus 6.718, which is 46.34 meters. So I plotted that here. So that's 1 second in total, the initial 0.5 seconds and the 0.5 seconds of deceleration here. So let's look at the next one then. We're going to look at 2 seconds in total, which is 1.5 seconds of deceleration. So I've done that here, 1.5 seconds of deceleration. S is equal to 125 over 9, which is the initial velocity, times 1.5 minus a half, 1.818, 1.5 squared, which gives me a distance traveled during deceleration of 18.788 meters. So therefore the distance remaining to the lights then is going to be 955 over 18, the total distance, minus that distance, which gives me a distance of 34.27 meters. So again, if we come back up here, we have that distance plotted here, or that displacement plotted here, after 2 seconds in total. Let's look at the next one. I've got 3.5 seconds of deceleration. So you just stick 3.5 into the formula here, and you get a distance traveled during deceleration of 37.476 meters. So the distance remaining subtracted from the total distance, and you get 15.58 meters. So that would be this point here after 4 seconds in total. Let's look at the last one I've done here, 5.5 seconds of deceleration. Stick in 5.5 and 5.5 in here, and you get 48.892. Subtract that from the total distance, and you get 4.16. So again, I plotted that here. Now, the last thing I'm going to do here is find where the graph will cut the x-axis. So in other words, I want a displacement of 0. So I want a total distance traveled during this deceleration, S in other words, as 955 over 18. So when I put that into my equation here, I get 955 over 18 on the left-hand side instead of S. The initial velocity again is 125 over 9. This time I want to work out what the time will be, the time when the graph cuts the x-axis. So t is here, I've got half here. Now in this particular case, I'm going to use as many decimal places as I can for the acceleration. So instead of 1.818, I'm using all of these decimal places here, and you'll see why in a second. And I've got t squared here. So let's just multiply across by 18. So I multiply this by 18, this by 18, and this here by 18. I get these three numbers here. This is effectively a quadratic trinomial, so bring everything over to the left-hand side. You will get this quadratic equation here. So all you've got to do now is put that into the quadratic formula. So it's minus b plus or minus square root of b squared minus 4ac over 2a. So we have a lot of decimal places here. What you'll actually find is that the expression underneath the square root symbol will be effectively 0, which leaves me just with 250 over twice 16.36 and so on. When you do that, you get t is approximately equal to 7.64 seconds. Now you don't get exactly 0 here. If I had more decimal places, I would become closer and closer to 0. But 7.64 is where it cuts the x-axis, and I have that plotted here. And that's really it for this question. It just says draw a displacement time graph for the motion and show your calculations. So I've done that. So this is part B. Two small spheres A and B of masses 3m and m respectively collide obliquely. The velocity of A before the collision is 3i plus 4j, and the velocity of B before the collision is minus 2i plus j, where the I-axis is along the line joining the centers of the spheres at the point of impact. The coefficient of restitution is 1/3. Show that the fraction of kinetic energy lost as a result of the collision is 5 over 24. Okay, so I've drawn what's happening here. This is mass 3m coming in here, impacting with mass 1m. So this is the velocity of 3m beforehand. This is the velocity of 1m beforehand. Velocities afterwards out here. The velocity in the j direction doesn't change in both cases, so it's just the velocity in the I direction that's going to change. That's 3i here, p here, minus 2i here, and q here. I've also written them into a table here. So the first thing we're going to do is we're going to look at the principle of conservation of momentum. So that just says that mu1 plus mu2 is going to be equal to mv1 plus mv2. So let's put in the values here. The mass here is 3m, and its initial velocity in the I direction is 3, plus the mass here is 1m, or just m, and its velocity in the I direction is minus 2. Afterwards then we still have 3m as the mass, and the velocity here is just p, and the mass here is m, the velocity here is q in the I direction. So we can cancel all these m's, there's an m in each term. Okay, so we've got 3 3's 9 here, minus 2, which is 7. And over here we've got 3p plus q. So that's our first equation. Okay, so let's form another equation then using Newton's law of restitution. So that's NLR. So this just says that the relative velocity afterwards divided by the relative velocity beforehand is equal to minus e. So in other words, p minus q divided by 3 plus 2 is equal to minus 1/3. So what we can do here is just cross multiply, and that'll give us 3p minus 3q is equal to 3 plus 2, 5. So that's just equal to minus 5. And that's equation number 2. So let's take equation number 1 multiplied by minus 1. That'll give me, let's see, minus 7 anyway here. And then minus 3p minus q, put a line underneath. I'll end up with minus 4q is equal to minus 12, or just q is equal to 3. So to find p then, let's pick one of the equations. Let's pick 3p plus q is equal to 7. This is equation 1. And we'll just stick in q. So it's 3p plus 3 is equal to 7. That'll just give me a value for p. If I bring over to 3, I'll get 4. So it'll just be 4 over 3. So now I have p and q. So let's just write down the two velocities afterwards. So the velocities after are for 3m, it's going to be 4 over 3i plus 4j. And for the 1m, it is 3i plus j. Now we will need the speeds as well to work out the kinetic energy. So I'll just do that as well. So the speeds here is just the square root of 4 over 3 squared plus 4 squared. And the speed here is just the square root of 3 squared plus 1 squared. In this case, we get 4 root 10 over 3, and in this case we just get the square root of 10. Now the speeds beforehand, speeds before are just the square root of 3 squared plus 4 squared. That's just 5, and that's for the 3m mass, and the speed before is going to be equal to the square root of minus 2 squared plus 1 squared. So that's just the square root of 5, and that's for the 1m mass. So I have the speeds before, the speeds afterwards, so let's just work out the kinetic energy. So the kinetic energy before is equal to half mu squared, so it's just 3m times 5 squared plus half the 1m times the square root of 5 squared. So when you do all of that, you'll get 40m. So the kinetic energy afterwards, same thing again, just add up the two kinetic energies. So it's half mv squared, so it's going to be half 3m times 4 root 10 over 3, which we've got the square, plus a half 1m times square root 10, that's here, square root 10, which we've got the square. Okay, so when you do that, you get 95 over 3m. Okay, so we have our two kinetic energies here. We have the kinetic energy before, the kinetic energy afterwards. So we need the kinetic energy lost. Kinetic energy lost is just 40m minus 95 over 3m. When you do that, you get 25 over 3m. So that's the kinetic energy lost. And what they are asking for is the fraction that's lost. So the fraction of kinetic energy that's lost is just 25 over 3, which is the amount that's lost. Divide that by the kinetic energy before, which was 40m. When you do that, you do get 5 over 24, which is what they asked us to prove in the question. Okay, so that's it for this question.